further ado, Matthias. Thank you, sir.
Thank you, John. Thank you, people from the organization. Oh, I have to get used to the microphone. And thank you all people for coming today, talking about thorium and all things related to energy. So I'm going to break with this promise to talk about thorium or rare earths. I'm going to tell you something about copper first, which is quite common actually. So let's see. So my name is Matthijs Bakkers. I'm from the Netherlands. I wrote 3 books. I run a YouTube channel, and there you can see my family, my wife and 2 sons, Huub and Luke. And I'm aspiring to become a nuclear communicator. I'm trying to explain people why we need nuclear energy. So first I'm going to share with you some of the local energy related stuff that is going on here. So here you see the Merrimack coal-fired power plant, which is just a couple of miles south from here. Oh, we zapped past the American Rush coal-fired power plant, but it looks the same because it has a huge black spot next to it and probably some smoke billowing out from a smokestack. So here's the Sioux coal-fired power plant. It's just a few miles north from here. And this one is particularly interesting because this is the New Madrid coal-fired power plant, and you see an aluminum production facility right next to it. That's about 20 miles south, I believe it is. And this one is interesting too because this is the Granite City Works. It's owned by US Steel. And on the right, you can see they have these tailings ponds, which they basically built into the river. And I don't know if you can see it, but there's a deep purple coming out on the north end, and there's light bluish coming out on the west end. So it's pretty nasty stuff. And here's the Phillips 66 refinery, which is just a couple of miles north from here on the Mississippi River. So my area of expertise, if I may call it that, is checking whether world-scale energy calculations are correct. That's the thing I try to do. And one of the biggest ones is, of course, Mark C. Jacobson's 100% renewable hypothesis. So I'm going to show you one of the things that he did that isn't realistic. So this here is a model. So they modeled like 30 years of energy production, and this here is in the late 2040s. And here you can see that Mark C. Jacobson expects to use about 1.3 terawatt hour. Oh no, I'm sorry, 1.3 terawatt of capacity to generate a delta of 1.3 terawatt hours per hour, so that it can offset the loss of wind energy or solar energy. Well, the problem is you only have 85 gigawatts of hydro capacity in the US. So expanding it up to 1,300 gigawatts, well, that's going to be a problem, isn't it? You don't have enough water, and you don't have enough place to put the dam. So you either choose to put valuable land on the water, or you seek a different solution, which there isn't. So 2 papers have been written to refute this nonsense. The first one is from Clack et al., or better, the first one is from Hurt et al., he was the first, and the second is from Clack et al. And I got the cue for the hydro argument from Clack et al. Because I missed it. When I first looked at the models, I didn't see it. I feel bad about it. So the next thing I want to show you is that here are 2 very prominent YouTube channels called Real Engineering and Minute Physics, and they have more than 4 million subscribers beyond them. And they were asking the question whether we can power the world with batteries. Well, the answer to the question is obviously no, because batteries don't generate electricity. That's the first thing to note. But the second thing is that they were wait a second, I need to get my notes now. So basically they said, well, if we built 100 gigafactories, each putting out 100 gigawatt hours of battery storage each year, then we can power the world. Now, the point being here that eventually, if we do that over the course of 30 years, we will have enough battery storage, if we can make it that far, to store about 3,500 gigawatt hours of electricity. So that's not enough. That's certainly not enough to power the world. On the other hand, if you look at lithium production, so if you want to create 10,000 gigawatt hours of batteries each year, you need about 259 tons per gigawatt hour of lithium. And we only produce about 36,000 tons of lithium per year over the entire world. So to get there, we need to produce 2.6 million tons of lithium just to get the production going. And that's not going to happen. We are not going to jump from 36,000 metric tons of lithium production up to 2.7 tons of lithium production. That simply isn't possible. And additionally, we need to do it tomorrow. So not in 10 years or in 20 years. We need it tomorrow. So this is the thing where my heart gets beating, because I like to do world total energy calculations, and these are 8 different models. So the red ones you see on the right side, those are decarbonization models by Greenpeace, the World Wildlife Fund, and the Solutions Project by Mark C. Jacobson, and they assume that we can reduce energy demand globally, and they assume that we can electrify almost everything, and what cannot be electrified will be powered by hydrogen, for which we use excess energy. I still don't see it in the graph where the excess energy is coming from or how much it is, but it seems to be there. So the lonely purple spike you see, that's the EIA prediction. And on the left-hand side, you see my status quo extrapolation. So I basically assume that the OECD and non-OECD are going to stay the same in per capita energy consumption, and then I extrapolated up to 9.5 billion inhabitants. So this is not the most probable outcome, but who knows? I think the EIA won't be that far off it. So I've written in red, much uncertainty whether we can actually electrify everything. So that gives us conflicting assumptions, because you simply don't know how much you can electrify. We can say, well, we can. You know, there's multiple ways of electrifying stuff. However, can we ramp up production figures for these things, etc.? It's very uncertain. I'm not confident saying, well, we can electrify everything. So we move on to copper, because copper is probably the most important, most basic element we need in energy production. So this is my area of focus. I focus on copper because it's the lowest common denominator, which has the first biggest hurdle to take. So, for instance, renewable energy is about 5.5 metric tons per megawatt. Nuclear and gas and coal is about 1/5 of that. So it's still a ton per megawatt, but it's less. So I want to find out how much copper we would need if we do a hypothetical 50-50 wind and solar energy mix. So first, I create 3 models, basically one in which we would consume 150,000 terawatt hours of energy over the entire planet, up to 250,000 terawatt hours of energy per year. And you can see it ranges from about 50 to 81 terawatt of capacity, wind and solar. And I'm giving wind and solar a very optimistic half terawatt of capacity by now, because, you know, it's probably less at this moment. And I'm not provisioning for any backup of any kind. I'm just going to imagine as if this is a perfect solution with, you know, the perfect energy grid, which will balance everything out, which is of course not possible, but it will make my modeling easier. So first we are going to look, well, it's a little arithmetic basically. So 5.5 tons per megawatt is the same as 5.5 million tons per terawatt. So 250,000 terawatt hours is 81.5 terawatts. And for 81.5 terawatts, if nothing happens in copper usage in renewables, so suppose the copper use efficiency, if you will, remains the same, we would need to extract about 454 million tons of copper, which is more than half of what we can economically recover right now. And I know that there's always this thing of demand and wait a second, I'm not an Englishman, so I need to find the word of supply and demand. So perhaps we can yank out that much copper within 30 years. Who knows? But I'm very doubtful that we will. And by the way, all my figures in this regard come from the USGS mineral yearbook. So here you see a very tiny version of my 3 models. It's 110 rows in total. It's 23 columns, and it has a total of about 2,300 data points. So, and in the end, I boil it down to this. So suppose we want to, I assume a copper growth, annual copper growth of 3.5%, 4.5%, and 5.5%, and allocate the surplus copper we have with regards to today to renewable construction. So you see, the best possible scenario is when we end up with using 150,000 terawatt hours of electricity, 50 terawatts of capacity, and we end up building about 18 terawatts of wind and solar, and we end up short with 32 terawatt hours of wind and solar. So this is busting, you know, building everything we can from here until 2050. So we're going to be in deep trouble if this is the path we choose, which is the path people like Mark C. Jacobson like to put us onto. So here's my conclusion. I think that 100% renewable shouldn't even be a thing, not in science nor in politics. I question whether 100% renewable proponents have actually attempted to create such simple models, because, you know, it's simple. If I can do it, any one of you can do it, because I'm not the smartest person in here. And then the final conclusion: how did this pass peer review? It still puzzles me up until today. So the peer reviewers must be knuckleheads. It's that simple. I'm almost finished. So here's my closing remark. This one is for Ed. I don't know where Ed is. There's Ed. There's Ed. So I'm all in favor of using all utonium or allotonium or allotanium. So this basically means what are we going to use? I don't care. Thorium, uranium, depleted uranium, weapons grade plutonium, whatever. We need. Let's see, because this is the kicker, right? We need, and I'm not American, so I can't throw this out at the top of my head. So here we go. It requires practical technological achievements from you. So we really need to get cracking on it. That's it. Thank you for
Thank you very much.
Yeah.
So we're gonna jump right to one of the best developments for this year is that the long-awaited molten salt reactor book, a compilation really of lots of different resources and sources, and it was put together, came out this year, and it was put together by the inspiration and leadership of Professor Thomas Dolan. So let's thank Dr. Dolan, and thank you very much, sir.
Do you know where slideshow is on this?
For PDF.
Yeah.
Just hit up or down arrow or page down, page up. Okay.
Good morning. The public is concerned about the cost of nuclear energy, the accidents that have occurred, and its long-term waste disposal. Molten salt reactors with thorium fuel can alleviate all of these concerns. I'll talk about the new book that's come out, Thorium Fuel, Molten Salt Reactor History, Solid and Liquid Fuel Reactors, Problems of Light Water Reactors, Development Issues, and Worldwide Activities. This is the new book that was published in June of this year by Elsevier. And I want to also recommend this excellent book by Bob Hargraves, Thorium, Energy Cheaper Than Coal. This is what awakened me to what's going on. And Bob will give a talk later in the morning. The first 3 chapters of the new book deal with motivation. Why are we interested in thorium and molten salt reactors? The next chapters 4 to 10 deal with technical issues such as reactor physics, thermohydraulics, materials, chemical processing. And you can see there are many authors of the different chapters. Then chapters 11 to 16 deal with generic MSR designs, the various categories. Liquid fuel with a thermal spectrum, liquid fuel with a fast neutron spectrum, solid fuel with molten salt coolant, static liquid fuel, accelerator-driven systems. Dr. Maineni will be giving a talk about that at this meeting, and fusion fission hybrids. Then specific reactor designs by Professor Dai from China, Dr. LeBlanc, who will speak at this meeting, Lars Jorgensen, Thorcon reactor, Klusterman, the semaphore, it's a European study of a reactor, and Ian Scott. More specific reactor designs, numbers 22, 23, and 24 all deal with using molten salt reactors to incinerate actinide wastes from present power plants. And then finally, the dual fluid reactor. Chapter 26 deals with activities around the world in 23 countries. Now let's talk about the thorium fuel cycle. As most of you know, if we absorb a neutron in thorium-232, it becomes thorium-233, which decays by 2 beta decays to uranium-233, an excellent fissile fuel. We want to avoid neutron capture in palladium-233 because that would spoil the breeding of uranium-233. 1 ton of thorium ore can provide enough energy to run a 1 gigawatt electrical year power plant. For uranium, it takes about 293 tons because you're enriching it to increase the fraction of U-235. And that also produces about 1 gigawatt electrical year. So the point is that you get a lot more energy out of thorium, a greater fraction of what's available. And the thorium abundance in the Earth's crust is 4 times the abundance of uranium. 1 ton of thorium costs about $0.3 million, and 500 tons of it could provide all of the electricity needs of the United States for 1 year. The thorium U-233 fuel cycle produces 4 orders of magnitude fewer actinides than the uranium-plutonium fuel cycle. This is from an article by Hargraves and Moyer in the American Scientist. So the blue curve here is the radioactivity of the fission products that decay in about 300 years. So this is a time scale at the bottom here, a logarithmic scale. There's 100 years and all the way out to about 10 million years. And by actinides, we mean those elements with Z greater than 89. So it's the actinides that cause the long-term waste disposal problem of today's reactors. If we hold things for 300 years, the fission products are virtually all decayed. Molten salts. If you heat salts up, they become a liquid. The melting temperatures of various salts are shown in this slide. At the bottom is sodium chloride, which has a very high melting temperature, so it's not suitable alone for use in a molten salt reactor. At the top here is the heat transfer salt, HTS, which are nitrates. That's used for solar thermal power plants and other molten salt applications. There are several industrial processes that use molten salts. The lithium fluoride, beryllium fluoride mixture called FLIBE was used in the Oak Ridge experiment in the 1960s. It has the disadvantage that it produces a lot of tritium, but it is also has good neutronics properties. A little bit about the molten salt reactor history. The U.S. built an aircraft reactor experiment in 1954. It operated at 2.5 megawatts at about 880 Celsius for 100 hours successfully. But about that time, they developed the capability of refueling bombers in the air so that it would extend the range, and they developed intercontinental ballistic missiles. So they felt that the nuclear-powered aircraft was no longer needed for military applications, and the project was terminated. In the 1960s, Alvin Weinberg and his colleagues at Oak Ridge looked at the possibility of breeding U-233 fuel from thorium and concluded that it looked very promising. Oak Ridge built the molten salt reactor experiment using FLIBE salt for the coolant with U-235 fluoride salt dissolved in it and Hastelloy structure. There's a nickel alloy that's developed especially because it's got low corrosion rates with the FLIBE coolant. It operated successfully from 1965 to 1969. Then the government terminated the MSR studies in the 1970s. As John Kutch remarked, this is an idea that was developed a long time ago, and now its time has come. This is the layout of the molten salt reactor experiment at Oak Ridge. The reactor vessel is there, and I'm sorry for you people over there, I can't show it on both screens at once. The primary coolant loop is in the center there, and there's a heat exchanger that goes to the intermediate coolant, and that's cooled by a radiator. There's a freeze valve number 13, which if the fuel overheats, the valve melts and the fuel drains into the drain tanks at the bottom left. This is the reactor core of the molten salt reactor experiment. The salt flowed up through the channels in the graphite, and it was a thermal neutron spectrum. And they were planning to build a molten salt breeder experiment following on to this, but the funding was lost. This shows the air-cooled radiator of that experiment. You can see the metal glowing red hot. Now, this type of cooling might be used for a commercial power plant. Charles Forsberg of MIT has proposed that the air could be heated and drive a turbine to generate electricity. So if you're in an arid region where cooling water is not available, that's a good alternative. Let's look at solid fuel MSR and then liquid fuel MSR. Solid fuel could be rods or plates or pebbles and would be cooled by flowing molten salt. The pebble design, the spheres would be 60 millimeter in diameter. That's about the size of a billiard ball. And each pebble would contain hundreds of tiny fuel particles. This is a tree-coated particle. It's about 1 millimeter in diameter, and it has several layers that prevent the fission fragments from escaping. Here's the layout of a fluoride salt cooled high temperature reactor called FHR. The core is down there. The pebbles are cooled by molten salt. There's a heat exchanger, an intermediate coolant loop that carries the coolant to an energy conversion system, a heat engine. It could be a Rankine steam cycle or a Brayton gas turbine cycle. There's also an auxiliary air cooling loop available. And at this conference, Professor Scarlett will give a talk about the FHR, I believe. This shows an experiment at Professor Per Peterson's lab at the University of California, Berkeley. The blue, green, and yellow pebbles are tiny plastic spheres that simulate the flow of pebbles in an actual reactor core. Now let's turn to liquid fuel molten salt reactors. Here's a schematic diagram. The core contains the fuel in yellow. There's an intermediate coolant loop with another molten salt in red. That might be the heat transfer salt. And then the power generating system. That could be a Rankine or Brayton cycle. And part of the fuel is extracted to the fuel processing plant, which will remove some of the fission fragments and adjust the reactivity, the content of U-233. And that fuel processing plant is really the heart of the system. It's a great chemical engineering development project that's in progress. Here's some light water reactor problems and the corresponding solution from molten salt reactors. We don't need manufacture of pellets and rods. There's no burn-up limit of the fuel. Continuous refueling. No boiling below 1400 Celsius. That would eliminate accidents like the TMI accident. It operates at low pressure, and there's no water or steam, so it would eliminate the steam explosion of the Chernobyl accident. There's no water or zirconium in the fuel, so no hydrogen is generated in the fuel. So we would not have any hydrogen explosions like the explosion that occurred at Fukushima. The xenon-135 could be removed continuously, so there would not be a need for large excess core reactivity to overcome the xenon poisoning. The fuel's already molten, so we would not have to worry about fuel melt. Some of the fission products could be removed continuously, so the core reactivity would be lower. Actinides can be recycled and incinerated. And much of the thorium energy could be utilized. And higher thermal efficiency would be possible because we can have the coolant at temperatures greater than 700 Celsius. So these are the economic advantages over light water reactors. No manufacture of fuel, high efficiency, low pressure means a thinner vessel, so it's easier to manufacture. Compact air-cooled Brayton cycle is possible. Startup using used light water reactor fuel. Enrichment plants are not required, and fuel burnup is not limited by radiation damage. Environmental advantages, recycling of actinides, less fuel waste, less rad waste, less waste heat rejected. There's already 3,700 tons of thorium available, and it's 4 times as abundant as uranium. Here's an example of a liquid fuel design. Okay, well, I'll just go through this then. The point here is that Thorcon reactors or other reactors can be mass produced like a shipyard, and they require much less steel and concrete. The main development issues, chemical processing, materials, and the other things shown here. Tritium management techniques, I'll skip over that. Worldwide activities, the Thorium Energy Alliance organized this conference. The ITHEO in Europe organized the Mumbai conference, and there's other organizations as well. Here's some research activities. And China is the world leader. They have 700 people working on developing a solid fuel reactor and a liquid fuel reactor. So in summary, the vision, we envision a world with affordable molten salt reactors burning thorium, uranium, and actinides, producing electricity, hydrogen, and desalinated water with no serious accidents. Thank you.
Thank you very much, Professor. I'll show you the book. It's a book that Professor Dolan was responsible for assembling, herding a lot of cats. So thank you very much, sir. Appreciate it. We're sort of dynamically updating how we're doing things here. So we're gonna have Robert Hargraves come up and give a 10-minute. You saw a little bit of there. Robert Hargraves is gonna give a little 10-minute primer on Thorcon and where they're at these days, and then we're gonna jump to the break. Professor Naoki Takaki was very kind, and we're putting him on tomorrow's schedule. So I don't even know why we print these things, because it's like we got stock in trees or something like that. So we're trying to accommodate the loss of a lot of our folks here.
Is Bob doing the radiation?
Yeah, Bob, you're doing the Thorcon, right? Thorcon update? So, this is Robert Hargraves. Many of you are familiar with him. I'll let him introduce himself.
10 minutes and we'll...
All right, we'll do it. And so how do I advance the slides?
Oh, just either the up and down key or the page down. There we go.
We have 2 objectives, as you can see. Not only to solve the global warming problem, but to solve the problems of the developing world that desperately needs more energy to approach the lifestyle that we have. This cover picture, just for a minute, is a CAD-produced diagram of our design. The power plant itself, the fission plant, is underground, as you can see. On the left side, we'll talk a little bit about the passive cooling that we have. That's just in the event that we need to reduce and remove the decay heat on the loss of many other parts of the system. The turbine generators are just standard ultra or supercritical steam turbine generators. They're above ground. They are to be purchased competitively. We need to have access by ship to change the cans every 4 years. So we are committed to being near an ocean port or up a river. First thing to notice is that world electricity use is going to increase. This chart shows world electricity. Look on the left. That is on the bottom, the number of people in North America. Horizontally on the vertical axis, the average power consumption, in our case, 1.5 kilowatts. So there shows you the 528 gigawatts of average power consumed in the United States. Looking across the rest of the world, we see there's a great gap of power just even to achieve the level of electrification that we have in Europe. Our marketing objective for Thorcon is Southeast Asia, starting in Indonesia. But you can see the great opportunity there in population and a growth opportunity. This is not well known to us, but it's well known to all the economic development experts in the developing world, and that is electricity is crucial to prosperity development. Each dot represents a single country. We are relating here the vertical scale, which is per capita electricity consumption, to per capita GDP, which is closely related to income. They are closely related, about $5 of GDP for just 1 kilowatt hour of electric power that costs about a nickel. They know that. They want more electricity. We know that in some of the areas around Jakarta, there are industrial parks that are empty because of a lack of power availability. However, the developing nations do what they have to do. They can't afford to buy trillions of dollars of solar panels and windmills that only work part-time. Therefore, they choose coal-fired plants. This is not a projection of coal power plant construction. This is a list. It adds up to 1,400 gigawatts of new power plants. Some of those in that list are on hold, and there's competition there from natural gas. So although we've been building about 2 coal plants a week, the natural gas industry is trying to steal that, and they're going to build approximately 1 power plant per week worldwide. That is the industry projection for combined cycle gas turbines. There's a problem, and that is the more coal and natural gas that we burn, the more CO2 is put into the atmosphere. Some of it dissolves in the ocean. Lots of it stays right in the atmosphere, increasing the opacity to infrared radiation and increasing the temperature of the Earth. Here on the left is one of the charts about the various emissions pathways, and they've stopped calling them useful things like business as usual, but the IPCC in their scientific genius calls it now the RCP 8.5 pathway. Now, also I discovered that parts per million is hard to understand, so if you multiply by the weight of the atmosphere, we can find out that we're likely to reach that high level of emissions with adding 5,000 gigatons of CO2 to the atmosphere. And the right-hand side shows the various temperature increases above nominal that will occur with these various pathways. But the point is, business as usual, 5,000 gigatons will add 4 degrees centigrade. That's a lot. Now, the other thing to notice is let's look at an individual power plant. An individual power plant emits about 8 megatons of CO2 per year. And you can just do the math, look at the coal that you're burning. If we really build 1,400 new coal power plants, we're going to emit 11 gigatons of CO2 per year into the atmosphere. Now, the IPCC has something called a gap analysis. The IPCC says, well, if we follow the current committed policy for reducing CO2 emissions, we will emit in the world 59 gigatons per year. That's not even business as usual. This is assuming all the commitments that people made prior to Paris are complied with. If we look at the Paris cuts themselves in the gap analysis conducted by the IPCC, it says Paris will cut out 4 gigatons per year. So all of you folks who think that we were unwise to leave the Paris Agreement, you may be correct, but the Paris Agreement is basically meaningless compared to the problem that we have. If we look at the Thorcon cuts, if we can literally replace 1,400 gigawatts of coal power plants, that alone will avoid 11 gigatons per year of CO2 that is to be added to the atmosphere according to the list of coal plants under construction and proposed. The 2-degree cuts are, it's funny how the slides are formatted differently on different people's computers. The 2-degree cuts that the IPCC says will in fact require cutting back by 18 gigatons per year. So we're not even close to getting that. We're way off. Will renewables do it? Well, you just heard one talk that says worldwide wind and solar, water, wind, and solar 100% by Jacobson won't work. Well, we know it won't work. I mean, Google spent that much money on it, and they concluded in this article in Spectrum, it won't work. People love green, but they're not rational. You've got to help. Whoops, this doesn't show either. Our mission basically is cheaper than coal. We feel and believe that the only way to convince the developing nations to adopt a less expensive, cleaner energy source is with economics. If we can provide them a clean, safe, full-time opportunity for inexpensive power that they can rely on, they will adopt liquid fission instead of coal because they can get more of it for the dollars they have to spend. They're not so afraid of nuclear power as we are. There are 50 under construction in the developing world now and 150 planned. If we can provide them with the liquid fission opportunity, instead we have an enormous market ahead of us and also available to all of our competitors in this room. And you're welcome to find these slides. I'm sure John will post them. There are references to these sources in the notes fields. You probably know this principle, or maybe now I'll just review it for a minute. In the Thorcon world, there's a can, the red thing in that diagram. Inside that, there's the reactor vessel itself that contains the molten salt and the moderating graphite. There's a molten salt reactor pump above, a heat exchanger that exchanges energy with a secondary salt loop. Near the bottom is a safety drain tank into which we can drain the molten salt in the event we need to do a cold shutdown for any reason. Okay. Stop. I'll quickly wrap it up. Sorry. Anyway, you know the background here. We're working closely with Indonesia. We did a pre-feasibility report. We're proceeding on to a technical assessment with them. So this looks pretty good to us. Our idea is to have it in a hull that's to be floated to Indonesia, settled, and commissioned right there. Here's an artist's, well, actually a CAD diagram of 2 Thorcons being serviced by a ship. That's where we sit with Thorcon, World Energy, Climate Change, and Indonesia. Thank you.
Thank you. Thank you, Robert. Thank you, Bob. Appreciate it. Very good. So I'm going to let you guys off the hook for a minute here. I'll give you like the schedule says differently. Just ignore that. Give you like a 10-minute break to go and fight each other over the bathroom, and hopefully we can see you back here in about 10 minutes, or at least I'll start harassing you heavily in about 10 minutes. folks, if you could start finding your way back, I sure appreciate it. And I know the funnest thing about these conferences is to talk to each other, but if you could just try and mosey on back to your approximate location of sitting and residing for the duration here, we can all tough our way through this and God damn it. I think so, but we'll just say Bucknell or
presentations. And there's two of them. One from yesterday, one from today. Because you know I can't not add it. Where's the flip? Shit. Yeah, except for it's still split. There you go.
you piece of shit. All right, everybody, we're going to see how relatively on track and somewhat retain the order. So I'd like to, I'm going to give you one more minute, and I'm going to give you people in the hallway. So put your thinking caps on. If you want, I'm going to let, while you do that, I'm going to let John introduce himself real quick.
All right, thank you. Thank you for the introduction, John. My name is John Bucknell. I'm a professional engineer. Am I on the mic? It sounds like I'm on the mic. Great. I'll put it a little higher since I'm taller than most presenters. I've spent about 25 years in the automotive and aerospace industries, but those aren't my passions. If you look me up on the internet, you're going to find most of my publications are on the subject of nuclear rockets. One of the few people actually working on the subject matter. But obviously I'm here today to talk about nuclear power. Energy conversion is something that I've spent my entire career on. And despite the fact being a rocket scientist, I'm going to give you an economics presentation, so hopefully you can stay awake through it. But I promise that there's a payoff at the end about the whole shebang. So we're good to go. And as you can see, the topic of my presentation is how to improve the economics of your nuclear power plant. We've talked a little bit about the needs around the world, and so we're gonna jump right into it. So we're going to talk about world energy consumption. Some of the earlier presenters talked about electricity in particular. I'm going to talk about the whole world's energy consumption, what that and how that impacts us in our planning. Talk about the impacts of renewables. Talk about levelized energy cost, which is how much it takes the producer of the nuclear power plant to actually sell the electricity or other energy products without losing money. And then a proposal on how to leverage these forthcoming high temperature nuclear reactors to produce energy storage. So obviously we're all here because we think that thorium in particular and nuclear in general is a safe, low-cost energy source, and it's vital to future humanity if we're going to bring all of us up to the same level of expenditure on energy that we have in North America. Also, we want to have that energy distributable so that no one person controls it, no one organization controls it, so that we can have ongoing prosperity for all. Again, nuclear probably is the best bet for doing that. What we want to do is to make sure that the economics of the nuclear power is addressed most beneficially for all. So the topic is to change the paradigm a little bit about how to build your nuclear power plants. If you build a nuclear power plant capable of producing many product streams, you probably want to build them at maximal capacity. So you don't want to build them just for base load. You want to build them as big as you can and use that excess energy to create chemical energy storage. So this chart is probably the most informative. Right now, primary energy consumption, so that's the type of energy that is used to convert to your end product, is mostly fossil fuel. As you can see, about 85% as of last year. Nuclear accounts for about 5% of that total worldwide. And if you look at how those are consumed in a final form, electricity is only about 20% of the total. The balance is used directly for heat or motivation or some other factor. Electricity is just a small part of the picture. In fact, there are areas that struggle a lot with electricity. Transport in particular is about a third compared to the other sectors that are consumers. If you look at the chart on the right, you see that of this third of total energy used, there are some areas that are primarily the heavy-duty consumers that can't be electrified. We've talked about hydrogen as an energy source for those consumers, but designing aircraft even around a liquid hydrogen is a challenge. Commercial air, really we have no technical solution for anything else other than hydrocarbons right now. And that's also true for marine, heavy-duty marine, and even over-the-road trucks. There is really no solution set that gets you to electrification. So we need to continue to have chemical energy storage for these consumers for a long period to come. Now, as you might be aware, there's seasonal and daily variation in energy consumption on the electrical side. If you build a baseload plant, you can operate that plant all the time. 90% capacity factors are not unusual for nuclear power plants. However, there's a 30% variation from hour to hour, even during the summer, which is generally the highest consumer. And if you build a peaking power plant to cover that, it's only going to operate about half the time, a little bit more. And if you build a power plant in smaller markets that needs to cover the entire energy demand during the day, it's only going to be able to run about 80% of the time because it has to load follow. And in the presence of solar, it gets worse. If you assume that 10% of your energy demand is covered by solar power, you start worrying about the energy storage problem. In this case, you can see that the numbers change a lot. Your peaking plant can only run about a third of the time. And even if you have baseload capacity, it's only going to run about 60% of the time. The projections that solar power is going to cover more than 10% of the total energy demand are quite a bit higher than that. So some planners would like to go to 50%. So that makes this problem even worse. And thankfully, there's some publications out there on nuclear power on how much it costs to generate. But most of them talk about 90% capacity factors or better. Thankfully, the Energy Information Administration publishes estimates on Gen 3 nuclear power, and this is the AP1000 on the left. And you can see that it makes about 10 to 11 cents per kilowatt hour at 90% capacity. But if you run it lower than that, it can triple the cost of energy, all the way down to 30% capacity factors. Thankfully, Thorcon has the most detailed executive summary on finances ever published, and I thank them for that so I can do this analysis. Their projections, of course, are to get the cost of electricity down about 5 cents per kilowatt hour, which is great, but even still, if you run at lower capacity factors, those numbers can almost double. But the biggest takeaway is that these costs are driven by the amortization, the finance costs of the production, the building of the plant themselves. And I'm using pretty conservative numbers for these projections. So they assume a 20-year finance period with a 10% interest rate. Now those are both maybe on the high end of what you might expect for a utility scale production, but we're just using this for a frame of reference. So the other half, most of you might have heard of the sulfur iodine energy conversion cycle, which extracts hydrogen from water. You need a high temperature energy source to do so. Particularly, you need about 900 C. In fact, when nuclear was in its heyday, NASA published this solution set in 1976. And the reason for that is that you can use your energy source through CO2 recycling to make chemical energy, and that CO2 that you produce, even when you burn the chemical energy storage at the end, recycles itself right back in the atmosphere. And in the chart, this arrow on the lower left, if you can see my cursor, the atmosphere and the ocean are both in equilibrium with each other. So you increase the concentration of CO2 in the atmosphere, it goes right into the seawater. In particular, we're going to talk about thermochemical cycles because that's the one that's most favorable with high temperature nuclear reactors. So talking about the capacity for turning nuclear energy into storable chemical fuels, General Atomics has done a lot of work on the analysis of this chemical process. It's quite complex. You can see this chart showing the yield of hydrogen as a function of the energy input and as a function of the process temperature. And this is the energy that's coming from the reactor itself. They did a study assuming they could get about 827 C as their source temperature. However, most molten salt reactors are planning about a 700 C peak. And that's for a variety of reasons. Some of them have to do with the negative temperature coefficient and the safety aspect of the reactors. At that temperature, the sulfur iodine cycle only yields about 10% of its energy in hydrogen. The good news is there's a solution, and this actually comes from the nuclear rocket world. This is called a turboinductor. It's a form of heat pump. It's a turbo machine that takes a portion of this product stream, which you can see in pink here, and spins a turbine with magnets on the end. And those magnets are spinning past a tungsten fin, and they are able to inductively heat that tungsten. So the product flying on the periphery, which is in green, is heated up quite a bit. In the nuclear rockets, they're trying to get above 3,600 degrees C, which helps your efficiency of your rocket. But in this case, for energy conversion, you can push your molten salt reactor temperature up to 1,000 C. This chart is actually a process yield assuming a turboinductor as your heat pump. And you can go from that 10% conversion efficiency to about 51% if you can get 1,000 C process temp peaks. So my proposal is a cogeneration plant. It's a combination of a 50% efficient MSR plant using a combination of Brayton and Rankine cycles to get that efficiency up. And then that chart from the prior slide is a 50% efficient sulfur iodine conversion plant. So you can see those numbers are strangely well matched. You can get the same amount of electricity or hydrogen for the same amount of energy input. And then at the end, I've tacked on a methanol synthesis plant, which is able to take that product stream and turn it into an easily storable and transportable form of energy. So to zoom in, this isn't any specific solution set. Any of the high temperature molten salt reactors will work fine. I've drawn a fly-based solution, which is again running about 700 C, and using a Brayton cycle to convert that from a primary source. The only reasons I choose Brayton over supercritical CO2 is the overall pressures are about half. And in this case, you run about 3 identical turbo generators. I'm a turbo machine guy, and this doesn't scare me at all. Some people are scared of turbo machines. This is really quite straightforward. But the big thing is if you have online chemical recycling, your plant can probably run all the time, 100% uptime. And if you need to service these turbo generators, you can shut down 1 or 2 at a time and continue to function as a chemical energy storage plant. So this is an attempt to get uptime as high as possible. Also, the Rankine cycle is running a refrigerant to recover the low-grade waste heat, and you'll see why that's important here in a moment. In this chart, it's the same as the one before. The heat leaves through the top, and I'll show you where it goes next. This is the sulfur iodine plant. It uses quite a complex process I'm not going to describe right now, but you can see in the center left the turboinductor, which is able to actively divert the heat from the high temperature loop that would normally be generating electricity into the generation plant, which is generating hydrogen. You can see the heat coming in from the bottom, going through the turboinductor, and then through the sulfur iodine plant. It comes in, distilled water comes in from the top, and then hydrogen. And as it happens, oxygen leaves going outwards. Lastly is the methanol synthesis plant. Again, methanol is my preferred energy storage solution, but there's lots of choices. Methanol is a feedstock for many petrochemical processes, so you can go from methanol to many other products, such as plastics. In this case, I'm showing a CO2 extraction from seawater. Any source of fresh water will do, but seawater is particularly important if you also want to do desalination. As it happens, this particular solution set uses the waste heat from the plant and is cooled by the seawater, and you get desalinated water for free on top of it. So the economics of this plant get even better. So this is my next to last slide. I just wanted to show you what this implies. This is all using the Thorcon economics that were published in their 2015 executive summary, also assuming a 20-year finance period with 10% cost of capital. Again, about 3 cents per kilowatt hour of electricity is a primary product stream, and using about a 44% conversion efficiency as opposed to the 50% I showed you earlier. The interesting bit is that these capacity factors on the left, as you go down, they're using less and less for electricity, more and more for chemical energy storage. You can see that compared to even our $40 per barrel oil prices, you can make methanol basically at parity. If I can get back to where I was. Where's my page up? You can get back to parity, which is in the lower right, with current gasoline prices. Even running your plant all for fuel production. So you're able to make chemical energy storage for the same price as our very low petroleum costs. Also to note, hydrogen is not cheap. There are plans to roll out fuel cell powered cars here shortly. If you have one or have had the opportunity to use one, you're charged about $16 to $18 a kilogram for hydrogen. Those are about what the prices for transport uses going forward. That's $419 per megawatt hour, so quite a bit more than what we're paying for electricity. This system is able to produce hydrogen at a tiny fraction of that. It's still about double the very low cost of natural gas we have today, but potentially it's a direct replacement for a lot of natural gas consumers. Okay, in conclusion, obviously, this is the same thing that we've all been saying. Nuclear can and should be a part of our prosperous future. And again, we want the lowest energy cost possible for all applications, for universal prosperity. To supplant the majority of end-use energy consumption, nuclear must be capable of economic production of product streams that drop in to many energy pathways today. This proposed flexible cogeneration plant will be able to produce product streams at or below current energy costs, with 4 out of 5 installations likely strictly replacing fossil fuels. And I didn't show this in the chart earlier, but the costs drop radically as the plants are fully capitalized. Let me just jump back to that to show you. The lower note here in the lower right, the first line, electricity at $14 per megawatt hour once you're fully paid off. Hydrogen at $6 per megawatt hour, and methanol at $12 per megawatt hour. These are fractions of what we're paying today. And it only takes 20 years to pay off these very conservative assessments of what the costs are. And I would even say the hydrogen plant and the methanol plant are probably more expensive than they would be for real once we learn how to do them. So that concludes my talk. Thank you for listening. I think I went super fast because I know we're all in a hurry to go see this eclipse. Do we have time for questions? You can answer questions. Yeah. Please, right here.
If you get a gigawatt of electricity for $2 billion capital cost, your cost more or less, and you then optimize nuclear for generation.
Okay, if I understand the question, how much capital above and beyond what you need for the nuclear power plant do you need for the hydrogen and the methanol plant? And then what are the, I think if I understand correctly, what are the costs going forward from that? Did I Okay, characterize it properly. Okay, so all these analyses assume that the plant for the methanol and the hydrogen are above and beyond the nuclear plant. The costs are, let me see if I can do this right. The cost of the methanol plant and the cost of the hydrogen plant are only about a quarter of the cost of the nuclear plant itself. And again, the product streams are, as I showed on the slides, but about the same amount of energy coming out as hydrogen as you would in electricity, if that helps answer your question. Yeah. Anyone else? All right. Obviously this is a rough draft. There will be a journal paper here toward the end of the year if all goes well. Oh wait, we got one more question.
Do you have a rough estimation of how long it would take to build all these facilities? Do you plan to build all at the same time?
Based on this analysis, I would argue you probably want to build them all at once. Your consumers are already there. If any of you drive flex fuel cars that run on E85, all that work to make them ethanol compatible is actually all the work that was done to make them methanol compatible in the early 90s. So the industry wouldn't be hard to go back to methanol, although you can convert methanol to gasoline, not too hard. It's all dependent on how easily the high temperature energy source becomes available. So I would argue that yes, if you want to displace all the fossil fuels, you probably want to go directly to the system that can replace it. So these are my ideas. No one else has seen it until today. So they exist. These technologies are not new, with the exception of the molten salt reactors, which are not very new. But as soon as those high temperature reactors are available, you can start doing it. Yeah.
I think we need to thank John for his analysis. Thank you very much. Thank you. I'll shake your hand, man. All right, thanks, brother. So now we're going to have Ed Pyle come and give us the lowdown on what he's been up to in his secret bat cave since leaving the Naval Reactor Program.
You can look my name up in the phone book later today.
All right, so just page up, page down, or arrows, and you're all set. Let's give him a hand. Thank you very much for coming, Ed. I really appreciate it.
I'm going to go down a little bit of a different route from what you're used to seeing in the molten salt reactor community. I decided that the best way to go to get the most flexibility and most safely and get something done today is actually to build a fast reactor rather than a thermal molten salt reactor. Yes, that's a little bit different, and I'm going to go over why that might be all right. So my name is Ed Pyle. I'm Chief Technology Officer and co-founder at Elysium Industries. Our base plant is 1,000 megawatts electric, 40% efficiency approximately, a chloride fuel salt, which is different than most of the ones you're used to, and a fast spectrum neutron flux, so higher fuel loads, what that means. But what it allows you to do is get to fuel flexibility. You can burn depleted uranium, low enriched uranium, spent nuclear fuel, reactor-grade plutonium, weapons-grade plutonium, thorium, and natural uranium. And we consume it basically to 100%, right? Existing water reactors burn 4%. If you burn the other 96%, that's a factor of 24 times as much energy left in that spent nuclear fuel. We're 25% more efficient because we're 600 C instead of 300 C, right? So that's 30 times as much just in the spent nuclear fuel. And there's 10 times as much depleted uranium already mined out there. So 30 times the existing plant life for spent nuclear fuel is about 2,000 years worth of fuel just for the spent fuel. And if you include the DU that's already been mined, that's 10 times that available. There's our core temperatures currently, low operating pressure as all the other molten salt reactors, structural components. This is kind of key. We are using existing nuclear qualified materials in our reactor. We are not going for something that is not already nuclear qualified. There's a lot of work done to get to Hastelloy to get the nuclear qualification. I think it has It might have ASME qualification, but I'm not sure if it's the actual grade that you would actually use or if it fits it within that grade specification. ASME does, yes. My question is, they've been tweaked and whether that's an ASME or whether the composition is broad enough to accept it, that kind of thing. And at this point, we don't want to have a power system that is developmental. So we're not doing supercritical CO2 unless it's actually been proven to be both doable, which it's not yet, and reliable. Because we don't want our power system to cause our reactor to fail. So we're counting on a steam power plant at this point. We might try to squeeze in a gas turbine if we can. So, flexible power. Right, so I said our base reactor was 1,000 megawatts electric. Right, that's 8 loops, compact heat exchangers, as you see there, 8 pumps, 1 pump in each loop, and full flow pumps all the time. Basically, there's going to be 1 large turbine or 8 small turbines. That starts to sound like NuScale, right? NuScale has 1 turbine per reactor plant. We can have 1 turbine per loop if we wish, right? That allows us to scale. It allows, if the 1 turbine goes down, allows you to stay up at power. And I'll get into that later too. But you can scale down, if you go down to 2 loops, that's 1/4 of the power, 250 megawatts. If you go down to 2 loops and half the pump flow rate and half the heat exchanger size, it's 125 megawatts. And on down, you can, basically the reactor is sized for criticality. It is just barely critical all the time, right? So there's no scale up, scale down for the reactor because it's just the minimum amount to stay critical. The flow rate through it determines your power rate, right? And then the heat exchangers that are attached to it and the pumps that are attached to it can be changed out, go up in power and down in power by making the flow rate higher, the pump's bigger, the heat exchangers bigger, or number of loops for that matter. And well, I said superheated steam, but it could be supercritical steam too. The problem with supercritical steam is it increases the cost of the power plant. But in a coal plant, they would go to supercritical steam because it saves them on fuel. Our fuel doesn't really cost anything, so I'm not sure we can justify the supercritical steam cost, the plant cost. Reactor types. The one that I've been showing is the loop plant. The pipes go out of the reactor. Most of the molten salt reactors and most of the small modular reactors use the one on the right, which is an integral plant. The problem I see with the integral plant is you can't do maintenance on it without doing an enormous amount of tear apart to get at components that are lower down, all right? So I like either the loop plant or the modular plant. Now, I'm dating myself here. This is the original definition of modular plant, right? Where each component is a separate module. The current definition of modular plant means you can ship it down the road as one reactor, which actually is not possible except for liquid-fueled reactors. But I'm not going to go into that here. We can talk afterwards. Right? So I like the modular plant the best. So that's where I prefer to head on that. The loop plant is the easiest one to design, though, today, at least in the United States. Right? Fuel chloride salt chemistry. The fuel salt, the functions of the fuel salt. Solvent for the nuclear fuel. We're going to end up with somewhere in the neighborhood of 30% heavy metal chlorides in our fuel. You need it, right? It's a fast reactor. The cross sections are lower at higher energies, so you need more fissile material. You need more fertile material to convert into fissile to get that. All right? It's the working fluid for transporting the heat out, and it needs to prevent the release of fission products. Most of the fission products, except for xenon, krypton, are chemically bound in the chloride salt. So even if you had a leak, they're chemically bound, they're not going to be released, and you leak it out, it would freeze. That's standard molten salt technology. One of the advantages of the chloride salts, and the reason why Sandia uses it for solar salts, And why argon used it for pyroprocessing is it melts at about 300 degrees C, lower temperatures than fluoride salts of the same composition. All right, and lithium fluoride, beryllium fluoride, I think that's only 70 degrees delta, but chloride salts are still lower. But I wanted to go to chloride salts to get that lower melting point, to get away from needing highly enriched lithium, which is a proliferation problem, because lithium enrichment means you get lithium-6 enrichment, which is a weapons material. So I'm trying to get away from that and the tritium as well. The other advantage is Argonne National Lab already uses standard materials for that. There's a lot of talk about corrosion versus water. Salts are less corrosive than water if they're pure. Don't put salt in water, don't put water in salt, and you'll be okay. All right? Don't drive your pet car down the road when it's snowy out. That's essentially people preventing putting salt in water on their car. That's one solution at least. But the corrosion of chloride salts, chloride is less aggressive than fluoride or fluorine, and so it's less corrosive than that, and that's why you can get away with standard materials in using that. That's why argon does that. The other advantage is it's better for passive control and active control. We don't have the thermal expansion of graphite with temperature or the expansion and contraction of graphite over lifetime with irradiation to account for in our temperature coefficients and our void coefficients. We just have a liquid core. There's just a can full of a liquid that's enough to go critical at a certain temperature. And that's it. And so that pretty much guarantees you have a negative temperature coefficient under all conditions. I'm not going to go into detail, but the chloride chemistry, I mean, Kim would probably be able to explain this probably better than I can. The chloride chemistry is such that the electronegativity, the Gibbs free energy of the molecules is such that you can separate out most of the fission products without removing the actinides. So the actinides can be left in the core at all times. So our waste stream is just fission products and some of the carrier salts. But there are a few fission products that don't get pulled out because they're too close to actinides, and we leave those in. Things like cesium and iodine. They actually reduce our melting point of our salt, so that's a good thing. And I'll get into this a little bit later, but one of the reasons for starting up with spent nuclear fuel is it has cesium and iodine in it already, and that helps reduce our starting melting point. A lot of reactors, when you burn in fission products, melting point goes down with time. We want to start with as low a melting point as you can at the beginning of life. And that allows, but the decrease in melting point allows you to increase your delta T and increase your power rating with time from beginning of life to later in life. But we want to start out the high power from beginning of life. Enhancement of nuclear non-proliferation and safeguards for this. I already talked about that we can remove fission products only. So one of the big deals that the DOE and the NRC has with molten salt reactors is how do you count the actinides coming out of the reactor? How do you know that somebody hasn't stolen any? In our reactor, we essentially do a mass spec and a Raman spectroscopy and figure out whether there's any actinides in there and what level, but that's less than 1% of the actinides come out from that pulling out, and that's just a process loss. And I expect to be able to get that down much lower with a few other techniques. So the uranium and plutonium always stay mixed. They always stay in the reactor and never come out. The waste stream comes out. We actually reprocess the chloride, recycle the chlorides, I apologize, recycle the chlorides back into the fuel manufacturing process. The fuel manufacturing process takes chlorides to convert spent nuclear fuel oxides into chloride salts. in one chemical step, right? But you need the chlorides to do that. So we might as well just recycle the chlorides out of the waste stream back into the fuel manufacturer, since the fuel manufacturing is already radioactive, the chloride's radioactive, no big deal. And oh, by the way, I have somebody that already wants to buy the zirconium off of us too. The radioactive zirconium from spent fuel, because they can't figure out how to get it without somebody using the stuff on the inside. So feed-in starts, so the one fuel option 1 is essentially high-assay, low-enriched uranium, so-called HLEU. It's between 5% and 20%. That's the first option, and it's about 90% fertile, 10% fissile in that case, and it's between 10 and 20% enriched. The feed-in for HLEU, a started up reactor, is about 20% enriched, and that decreases with life as you burn in more plutonium. The problem with the HLEU is you need to have this high enrichment. But I can't drive an enrichment facility, because once I get this reactor going for a few years, I don't need the HLEU anymore. So the enrichment facility is not needed any longer. So I can't drive the long-term development costs of an enrichment facility that can go up to 20%. Let's see. And the other difficulty, 2 minutes. Okay, second fuel system. Plutonium and spent nuclear fuel. We use weapons-grade plutonium, reactor-grade plutonium, and that gets us straight into our normal chemistry, right? We don't have to worry about changing chemistry through life. All right, thorium. Since this is a thorium conference, I thought I'd talk a little bit more about that. Thank you, Jim, for pointing that out. Uranium-233 and thorium. If you look at the 2 red lines on the first curve, that's the fission cross-sections for that. So yes, in a fast reactor, you have low fission cross-sections, but you can make those work in any of the systems. But you'll notice the reason why this curve is on there is it also has the uranium-238 and the thorium-232 fission cross-sections. So you notice in a fast reactor, which is to the right of that red line is where we're operating, those 2 cross-sections come up, and for uranium-238, we get about 10% fissions. For thorium, we get about 5% fissions. That's like having a few extra free neutrons. The curve on the right is the number of neutrons per fission that you get. You'll notice the green line on the right, where we're operating in the fast spectrum, is way higher than the number of neutrons per fission in the thermal spectrum. That makes the neutronics much easier to account for leakage, absorptions, poisons, or fission products in the coolant, all right? But you'll notice also that the red dotted line to the right of that red vertical line is actually higher than the thorium, the uranium-233 neutrons per fission. So I can actually run this reactor on a fast spectrum burning uranium-233 and thorium in there. The other thing I can do is I can start it off on plutonium and uranium and breed thorium into 233 in the blanket. I won't go into that. Notional, and only notional, molten chloride salt fast reactor 2. Passive safety, pumps without electricity. I figured that out, how to do that, haven't done the development. Pumped draining, which means not a freeze seal, and a pump that doesn't need electricity to run, and drain faster than a freeze seal, which is the same thing. I've identified that. This was written earlier. This was just, shall we say, 2 typos or 3 typos in a posting and stuff. Allothanium and stuff. We want to use everything. And we can use everything. We don't want to discharge fuel. We want to minimize proliferations. We want to get to 1300 C or 2400 F, which gives us 60% efficiency in just about any process, heat, temperature, any process you want. 1300 C is, concrete is made at 1400 C. We can get the heat up to 1300 C, and then you use electric heat to get to 1400 C to do concrete type deal. And the last one is, don't shut down in a natural disaster. Reactors aren't the problem. It's not danger, right? The danger is people not getting medical care because they don't have electricity. I'll skip the summary because I'm out of time. Okay, thank you.
Thank you, Ed. We'll smash it. I'm sorry, I forgot about your finger there.
Yeah, he twisted my hand to get me, my arm to get me here.
It's like I extracted a fingernail and he caved. All right, so we're going to have one last quick little presentation from Alan Metzger. Alan is going to give us just about a 7, 8, 10 minute breakdown of the work he's been doing as the Illinois associate of Michael Schellenberger's bit of business there. So if, I'll try and switch over for you. Well, Alan, you can do the rest of your self-introduction there.
Okay, I'm Alan Metzger. I am the state coordinator in Illinois for Environmental Progress. And Environmental Progress is about a 1.5 year old environmental pro-nuclear organization. And from the website, Environmental Progress is a research and policy organization fighting for clean power and energy justice to achieve nature and prosperity for all. So we come up against Sierra clubs and NRDCs of the world all the time. So I'll talk a little bit about our approach. Okay. So we have a mantra. It's kind of unofficial, but we use it anyway. And our mantra is to defend. This is all having to do with nuclear energy. Deploy, demonstrate, and develop. So these are not like a sequential thing. We need to do all these things. We focus mostly on defending right now. So in defending some of the things we've done, we've had on the street 1960s style protests or demonstrations or whatever you want to call them. These are pictures from Chicago, where we were working to save a couple of Illinois nuclear plants from closing. And we brought it to the folks at the Environmental Law Protection Center, Policy Center, sorry. And they've been fairly anti-nuclear. We're right outside their office camping out and making sure that they know. In California, we took it to the Sierra Club and some other folks in their offices on a march. So we've tried to really publicize the fact that environmentalism really means you have to look at all the science, all the tools, and use the ones that are appropriate. And nuclear energy certainly was one of those. So a subset of where we've been, the states that we've worked in, Illinois, of course, California, really, of course. That's where EP is located. And I should mention that Michael Schellenberger, as John mentioned, is the president and founder of Environmental Progress. So we're still a pretty small organization, but we've got we've had presence in all of these states, and we've worked on saving the upstate New York plants from closing. That was some legislation that passed last year. And then Ohio, Pennsylvania, Connecticut, Massachusetts are things that are in the news right now. And there are others too. So, but these are just some of them. We've also sent letters, open letters, and had people like Jim Hansen sign them to the president of South Korea, to president of France, the new president of France, encouraging them to, and in Germany as well, encouraging them to not go forward with plans to eliminate or curtail nuclear energy in those countries. So you might be thinking, well, these are all, the things that we're fighting for, the things that we're talking about are light water reactors. They got designed, 50, 60 years ago. It's all the problems that we always talk about in every TEAC conference. We've got, all these atmospheres of pressure that we have to contain, and containment buildings that are expensive, and all of these things. But we really feel at Environmental Progress, we really feel it's completely important for us to be protecting and encouraging the current nuclear technologies that are deployable today and do what we can to support those. And the reason for that is that we need shoulders to stand on. Next generation technology really depends a lot on existing levels, or existing technology industries. The supply chains, the people that work on these things. We want people to get nuclear science degrees, and if there's no place for those people to go when they graduate, or if there's fewer places for them to go, then they won't pursue those, and we won't have the staff that we need to design, build, and operate the new generation of plants. So this is really key to our crowd here, and even though we kind of, again, we're focusing on existing technologies mostly, but we support it all. So. From a deployment perspective, we are also, the website has a lot of information about, and I would definitely encourage you to check that out, the website, environmentalprogress.org. We have been publishing findings about the summer build shutdown, the VC summer shutdown, where they were building 2 AP1000s, and now they put that on temporary, perhaps permanent hold, we'll see. And in addition to the 2 plants at Vogel that are not currently at critical risk, but are still at risk for being halted. So we're doing research and publishing information about that. Then, of course, demonstration. This is an MSRE picture. That's the only demonstration new next-gen reactor I could find a picture of. So here it is. It's not actually new, but we really need to do that. And then, of course, develop. So we don't spend a lot of time talking to or about these companies, but we know that you're all out there. Some of them have been referenced this morning already, and we're very excited about all of that. But we hope that the work that we do will enable the next generation to flourish and bring the world the things that nuclear energy can bring it. Again, environmentalprogress.org is our website. Please go there, consider supporting us financially as well, and take a look at all the material that's there. Thanks.
Thank you, Alan. Thank you so much. We're going to have a little bit early lunch, but we are just going to have Gordon here give you just, especially you video enthusiasts, just a 2-minute primer on how to make your own or where to find some files. I'm just going to let him have at it here.
Sure. The actual talk will be tomorrow, so I'm just going to say the talk is going to be about how to use the video files I have to roll your own video, and the video could be about nuclear power, it could be about molten salt reactors, it could be about thorium-powered molten salt reactors. It's supposed to be quite flexible, so there's about 7 hours of content here, and it's sort of pre-edited into what I consider to be useful chunks. So if you want to start copying the files in advance of my talk tomorrow, if you have a laptop with 400 gigs capacity, you can copy it all, or you can copy a subset, but it probably sucks to download 400 gigs through your home broadband connection, but you can do that if you want to. So if anyone wants the files, borrow the hard drive from me right now and start copying onto your laptop, or bring your portable hard drive over to my laptop over there and copy from my laptop onto your portable hard drive. I can help you do that.
Very good. Okay, so now here's the way the schedule is going to break down a little bit here. We're going to have a little bit of a am I hurting your ears? I'm sorry. It's usually my voice is like a small little bird that floats out. Anyways, so the way it's going to work is we're going to eat a little touch earlier than what the schedule says, so that some folks can either eat the buffet that's in the other room, or there's some sandwiches that are probably somewhere in transit, who knows. But there is a train trip for some of you involved in the next hour or two. The rest of us will have some other talks and videos and some fellowship, and we'll share some war stories. So one thing that I've been told to tell you, we are in St. Louis, where they love their air conditioning, so you're sitting in this heavily air-conditioned room. But when you step out those doors, it is literally 106 degrees outside, and it feels like 120. That's the Real Feel temperature guide. Look it up on your smartphone. So hydrate. Please do not come back dead. We need all the members we can. And, you know, for real, I mean, if you're not used to, you know, swamp weather, you're about to, you know, enter a world of pain out there. So that's that. You could either go grab some lunch through that door right where Alan is sitting, or you can walk around and the food is set up in that room. So thank you very much, and I will make further announcements as they are required. What do you need? No, we'll probably do a couple talks while people are away. No, people going to the eclipse may miss some talks. Okay, is that, you're cool? All right, yeah, all right. Yeah, so there. But not much, maybe one or two or something. They had to make an agreement that you can't take food out of here.